Good morning, everyone, and thank you so much for joining us today. The focus of today's webinar is the top 3 ways to maximize your plant's amine performance. Now, as you know, the amine unit is the heart of a gas plant, and when it's not running effectively, plant's availability and performance is affected. Now, first, let me tell you a little bit about the featured companies today. Nalco Water and BASF, both leaders in their fields, have formed a unique partnership to deliver the expertise needed for the reliable functioning of your amine unit. The Nalco Water and BASF partnership combines leading chemistry expertise with premier process innovation. With customized on-site service and digital monitoring and analytics, their comprehensive solution maximizes plant performance and uptime. Our presenters today are Andrea Merrick, Senior Marketing Manager Midstream with Nalco Water, which is based in Naperville, Illinois. Andrea has over 33 years of marketing and research experience across gas and chemical processing and has been with Nalco Water for 24 years. Prior to joining Nalco Water, Andrea was with BP Amoco and with Natural Gas Pipeline Company of America, which of course is now known as Kinder Morgan. And Jesse Santos, Technical Market Manager with BASF based in Houston, Texas. Jesse has 30 years of experience in and around oil and gas industries and 18 years in the field of gas processing and gas treating. Before joining BASF, Jesse owned his own midstream consulting business, as well as led the field engineering teams in Anadarko Petroleum's midstream gathering systems in 4 U.S. onshore unconventional well basins. We will be taking your questions following the presentation. If you would like to submit a question, just look to the right of your screen and you will see a section to submit those questions. And now it is my pleasure to introduce Nalco Water's Andrea Merrick and Jesse Santos with BASF.
Thank you, Peggy. You know, natural gas has really been reshaping the global industry. In North America, and even more so in the United States, we've really seen almost unprecedented growth. We really expect that we're going to see about a 30% increase in production by 2030. You know, we've already observed an increase in exports for U.S. Basic and intermediate chemicals, you know, that use a feedstock, natural gas as a feedstock or a raw material due to the low cost position. Natural gas will be the preferred energy source. We really expect to see, the EIA expects to see natural gas as a key growth, more so than any other fuel source besides petroleum through 2040. You know, in order to meet, you know, this increasing demand for natural gas, plants really need to be operating at peak efficiency. In a recent study, recent published study, producers identify that they're already increasing investments in efficiency and reliability. Those are key drivers in plant availability and operating efficiency. You know, the amine unit is considered the heart of a gas plant. You know, if this unit is having problems, the entire plant is affected, and it really compromises overall plant efficiency and operating goals. Problems can and do happen in the amine unit. Jesse is now going to walk us through 3 ways to improve your amine unit. Jesse.
Yeah, thank you, Andrea. Over the next half hour, I'd like to touch on 3 specific things you as a designer, operator, or support engineer can either review or change to maximize the amine unit operations in your gas plant facility. Let's begin with the #1 thing you can do: keep contaminants out. This entails first identifying the contaminants that can impact performance and reduce or mitigate their entry in the gas plant, and more specifically, the gas treating unit. To begin the discussion on contaminants, I believe we should first review the anatomy or makeup of the oil and gas gathering system. This should help us identify possible contamination and their entry points. This system is a system of network of pipes, meters, and processing equipment laid out across the drilling basin. Pipes are the small 6 to 12-inch flow lines of oil, gas, and water. Meters are for the measurement of well performance and the allocation of flows back to the landowner. And finally, field processing equipment made up of tank batteries, which separate the oil and gas produced and the water. They also store it. Compressor stations also exist for moving along the recovered wet gas and NGLs to the gas plant. And there are also field dehydration units that dry the gas to protect the miles of gas pipeline from corrosion induced by moisture in the system. Here's a better way to illustrate what I just described. I pulled this drawing from a Google Map search of an area just outside of Odessa, Texas. You can see the well pads or squares in the larger plot of the gas plant, and the gathering system is all that exists in that circle, that larger circle. It is what we just talked about, probably more than 1,000 unconventional horizontal wells, flowing to more than 100 tank batteries or so, which each contain vapor recovery units or small compressors connected to a larger compressor station and dehydration units, all flowing to the gas plant for more processing. So let's get back to the contaminants. I'll classify these contaminants as gases, in our case, trace gases, aerosols and liquids, and finally, solids that are going to cause performance issues if and when they enter the gas plant. The trace gases I'll speak of today is primarily oxygen introduced by pulling air into the vapor recovery units. Another category is aerosols and liquids. These are compressor lube oils that make it past the coalescing filters on the compressor skids, and methanol and glycol that is injected in the pipeline in the wintertime to prevent hydrate formation. And finally, solids that I'll group in the category of black powder, iron sulfide, and iron oxide. Now that we've identified them, let's explore how they enter the gathering system so we can best manage them. We'll begin with trace gases. Most gathering contracts limit oxygen to less than 10 parts per million. I've seen some as high as 2,000 parts per million, but with stipulations to maintain the oxygen levels to 0. One way oxygen can enter the system is from the vapor recovery units pulling air into the system. Let's go more into this entry point. Leaking or unsealed deep hatches on oil and water tanks that feed the vapor recovery units can pull air into the gathering system. Other than checking deep hatch closures and gasket sealings, one option is to recover recovered vapors from the oil prior to it entering the tanks and combusting only those vapors which could contain air. We can prevent oxygen from being a contaminant by separating recoverable gases from those that may contain air or vapor using a vapor recovery tower. So oil and gas and produced liquid exits from the well and after water is separated and is fed to the vapor recovery tower. From there, oil flows to the storage tanks and recoverable gas is pulled into the gathering system from the gas plant through the vapor recovery unit. Any air that is inadvertently enters the storage tank through deep hatches is kept separate from the vapor recovery gas and is combusted along with the other storage tank vapors. Sounds like a solution, right? Well, not exactly. Variability in drilling activities will drive oxygen level spikes. This is attributed to new wells coming online and commissioning of field processing equipment like new tank batteries and new compressor stations. So we can minimize oxygen in the gathering system, but probably never eliminate it. Oxygen still enters the system. Now let's talk about the next contaminant, oil, aerosols, and liquids. We can minimize lube oil by maintaining coalescing filters that exist in the compressor skids. And for the injection of methanol and glycol, we just need to use them sparingly and ensure that we have adequate field knockout vessels to capture the excesses. Our final contaminant are solids like iron sulfide and iron oxides. We'll discuss how this is formed and how to minimize the formation. Let's start with iron sulfide. It can be identified as a sticky, gelatinous substance, or even a very fine black powder. If there is hydrogen sulfide in the sour gas, iron sulfide will form from corrosion of the steel pipe. However, if the gas does not contain iron sulfide still may form in the presence of sulfate-reducing bacteria. Additionally, iron oxide can also form from an acid-producing bacteria. These bacterial organisms thrive in areas where flow becomes stagnant, like well test separators, which are only used a few days a month to test the wells on the pad. Is bacteria creating your black powder in your upstream gathering system? If so, you can characterize them and apply the appropriate biocides to minimize the resulting black powder. So far, I've talked about minimizing the entry of trace gases, liquids, and solids. Now, let's talk about how to prevent those liquids, aerosols, and solids from getting into the gas plant and the amine unit. The best prevention is a 3-vessel inlet gas filter. First, a subcatcher to catch the free liquids, water, compressor lube oils, and any picking slugs. Second, an inlet receiver that is capable of removing mist and aerosols down to 100 to 150 microns. And finally, a high-efficiency coalescing filter that will remove pretty much everything else. Do you have all 3 in your gas plant or just one? The first step in maximizing your amine plant performance is keeping contaminants out. We do this by identifying the contaminants, minimizing their entry with equipment like VRTs, vapor recovery towers in the field, and inlet gas filtration at the gas plant in fence line. Finally, minimizing the formation with a chemical program using biocides. The second way to maximize your amine unit performance is to understand the role oxygen plays in amine unit corrosion and knowing what to do about it. Oxygen is capable of causing significant capacity equipment and reliability problems if its presence is ignored. Let's go over the impact of oxygen on the amine solvent capacity and the equipment reliability. Oxygen, even at trace levels, degrades the amine solvent and forms heat-stable amine salts. These salts form bound amine, so it is unable to absorb new acid gases and results in a capacity loss of the solvent and the entire plant. These degradation products exist as amine formates, acetates, oxalates, bicene, which is an amino acid, and a family of other amine compounds. These amine salts also increase the corrosivity of the solution. Finally, heat-stable amine salts drive corrosion, which produces iron sulfide in the amine solvent. These iron sulfide particulates often increase foaming tendency of the circulating solution, and at a minimum increase operating costs by driving up the frequency of mechanical filter changeouts. The newly formed heat-stable salts, bicene and other amine compounds, make the amine solvent corrosive, more corrosive than what the unit was originally designed for. For example, bicene, the degradation of methyl diethanolamine, is an amino acid. It has also been determined to be an iron chelant. This means if there's any hydrogen sulfide in the gas that has created some iron sulfide layer on the carbon steel vessels and piping, that iron can be chelated by the bicene, and the resulting bisulfide will form more iron sulfide, which is continuing the corrosion path. Amine units carry a designed-in general corrosion allowance of an 1/8 inch or 125 thousandths of a inch per year over a typical 25-year plant life. However, Bicene can accelerate that corrosion in localized areas of the plant to much greater than 5 mils per year. This often leads to pipe wall thinning and leaks in the hot lean areas of the amine unit. Oxygen accelerates the corrosion in the amine unit past the designed-in corrosion allowance. The combination of solvent degradation and increased corrosivity leads to amine losses, localized corrosion, higher operating costs than budgeted, and lost operating revenue from unplanned downtime. So really bad things happen when oxygen is present in the amine unit process gas. What we can do about trace levels of, what can we do about trace levels of oxygen in the amine unit? We can monitor and control. We should monitor the feed gas with an online analyzer, as well as monitor the amine solution for heat stable anion salts and metals, which indicate corrosion activity. We should also monitor corrosion with corrosion coupons. And finally, we can control the solution corrosivity by using a corrosion control program. So far, we have discussed keeping contaminants out of the gas plant and not ignoring the impact of trace oxygen in the process gas. The last way you can maximize your amine plant performance is to select the best amine for both your current and future needs. Of the most widely used amines in midstream gas processing industry, diethanolamine, aminodiethylene glycol, methyldiethanolamine, and formulated MDEA or MDA blends are listed here with 4 common requirements. Acid gas removal capability or capacity. Is it efficient from an equipment standpoint? Stability or degradation with acid gas. Is it stable, or does it degrade with the common acid gases that I need it to remove? Selectivity and mercaptan removal. Will it remove the acid gases such as hydrogen sulfide, carbon dioxide, or mercaptans that I need it to the way that I want it to? Of these 4 categories, MDEA and formulated MDEA blends offer more capacity and solvent stability than the primary or secondary amines such as aminodiethylene glycol and diethanolamine. For the high gallon per minute or per 1,000 wet shale gas cases, the midstream industry treating requirements rely on deep CO2 removal solvents for NGL, natural gas liquids, and LPG production. Also, when ethane values drive ethane recovery, product treating becomes a gas plant requirement. In these cases, only formulated MDEA and ADEG satisfy this amine unit's operational requirement. So are you using the most efficient, stable, and flexible solvent in your amine unit? In summary, these 3 ways to maximize your amine unit performance are to, 1, keep the contaminants out of the gas plant. You can do this by identifying them, minimizing their formation, and minimizing their entry. 2, don't ignore trace oxygen in the gas process. I have an active amine program to monitor the feed gas and solvent regularly. Install a corrosion control program to be ahead of failure due to accelerated corrosion. And finally, 3, select the best amine solvent for your current and future needs. The most widely available solvents and the removal requirements in the midstream industry, formulated MDEA, MDEA, and ADEG should satisfy most all gas plant needs.
Thank you so much, Andrea Merrick and Jesse Santos. What an excellent presentation, and a lot of interest has been generated. We do have some questions coming in from the participants. This is coming from Todd. He wants to know if there is anything that could be added to the amine to correct increasing acidic levels, and is the only solution replacement?
Yeah, this is Jesse. So, Todd, yeah, I think you're suggesting adding some stronger base to basically accept the anions. And bases are added, or other additives are added to reduce the corrosivity of the anions that are present. You can do that, but at some point you're going to have to totally remove those and take them out of the system. The other option is to start removing those with online systems, or start to, remove parts of the amine. Initially, what I was talking about, most of these anions are produced from contaminants in the gas stream. So it's really important to minimize the contaminants that are coming in, and if it's oxygen, use a corrosion control program.
Okay, we have another question coming in, and they want to know how often should they have their amine system analyzed?
So if your system is relatively clean, so get a sample, and when you get the vendor to give you the results, if it's clean in a couple of months, you really don't need to have it analyzed more than once every 3 months. But if you see that you're developing heat-stable salts, if they're doubling from 100 parts to 200 parts to 300 parts within the first 3 months, then you need to really keep an eye on that amine system, and probably once a month have an analysis sent in.
Okay. Another question coming in. What type of equipment would you recommend for corrosion monitoring?
Excuse me, this is Andrea. Yeah, there are different types of equipment that are out there that can be used. Obviously, the most basic are corrosion coupons. We also have been using LPR probes, linear polarization resistance probes, in the amine unit with extremely good success. I think the real focus is, really have a program and be diligent about it, because, corrosion obviously can creep up on you, and then before you realize it, the damage is done. So really use corrosion control equipment and program based on your plant needs.
Okay, this question coming in from Mark, and it has to do with anti-foam. He wants to know what type of anti-foam he should be using, and that he's heard in some cases this might cause some issues within the amine unit.
Yeah, so over the last 30 years, or even longer than that, there have been several different types of anti-foam, but in the end, in my experience, it really goes down to two. It's either a polyglycol-based anti-foam, or the original that we've all used since the 50s is the silicon-based anti-foam. So of those two, I've seen plants that actually use a combination of both. I usually recommend focusing on the polyglycol base because it actually works more as an anti-foam and not a defoamer. So the defoamer is more of the silicon-based anti-foam, which they call anti-foam. And if you've got a foam problem, it knocks it down instantly, but it does little to maintain the low foaming tendency of the amine, because it gets absorbed by the carbon filter and it falls out in the reboiler, polymerizes. So a true anti-foam was more, you should look more toward the silicon-based anti-foam, the polyglycol-based anti-foams.
Okay, and a question for both of you. This, of course, agreement and this partnership between Nalco Water and BASF, this is quite a partnership. It's very unique. What was the driving factor for this partnership in amine?
It's a great partnership. Really it's a marriage that was made in heaven, if you will. We both companies made a strategic move to partner together in the space, and really from a Nalco Water perspective, We really have a complete portfolio around the entire gas plant. And BASF really completed us with respect to bringing in the Amine, their expertise, combined with our service. So it really, I think, was a great thing to do. You have a comment, Jesse?
No, I think that you're right. We in BASF, you know us as world leaders in gas treating and LNG processing, or the pretreatment of that for large systems outside the United States. Nalco was an organization that we chose to help us help you bring the amines into the midstream business here in the United States.
Mm-hmm.
Okay, and I guess if someone would like to get more information, perhaps from you, Andrea, they would go to midstream@ecolab.com?
Correct.
Okay, as folks, as you see that on the slide. Thank you so much. This does conclude today's webinar, and a very special thanks to Andrea Merrick, Senior Marketing Manager Midstream with Nalco Water, and of course, Jesse Santos, Technical Market Manager with BASF. Thanks to all of you for your interest today. Have a wonderful day.